So let's start by picturing a classroom, like a totally standard, modern high school math class.
Right. Could be anywhere.
Exactly. Maybe it's in Botswana or Ghana or South Africa or, even right down the street from where you're listening right now.
Yeah.
And there's a teacher at the front, chalk in hand, writing out this really complex geometric proof or an algebraic equation on the board. And the numbers are super clean. The lines are totally straight. And there's this underlying message, right? Whether the teacher actually says it out loud or it's just kind of implied by the textbooks.
But this system, like this hyperlogical language of math, was handed down from a very specific place.
Right. Usually ancient Greece or Renaissance Europe. That's the narrative we all get.
That's the standard, yeah. The purely Western triumph.
Exactly.
Wow.
And because of that framing, a lot of students just feel this massive disconnect.
Oh, absolutely.
In fact, we are doing a deep dive today into this incredibly comprehensive book. It's called African Mathematics, From Bones to Computers, by Mamokgethi Satati and Abdul Karim Bangura.
It's a fantastic source.
It really is. And they highlight this massive World Bank study. They looked at students all across sub-Saharan Africa who were really struggling with science, math, and IT.
And the reason why is so telling.
Right. The primary reason was that they felt the curriculum was just entirely disconnected from their daily lives.
It felt foreign to them.
Like it belonged to someone else's culture entirely.
Which is just, it's a profound irony.
A huge irony.
Because, as we're going to explore today, the very foundations of the mathematics those kids are struggling with.
Yeah.
Like the underlying logic of the computer screens they're staring at or the geometry they're trying to memorize.
All of it.
It was largely pioneered right there on the African continent tens of thousands of years ago.
And that is exactly our mission today. We are going to completely reframe how you think about the history of human calculation.
It's a huge journey.
It really is. We're starting with ancient artifacts, moving into spoken language, looking at village architecture, scaling up to, the bureaucracy of empires.
Eventually ending up in the dirt on the side of a road.
Yes, playing a board game that literally rivals a modern supercomputer.
And the guiding principle we have to keep in mind the whole time is this. Math was not invented in a vacuum.
Right, not just someone staring at a blank piece of parchment.
Exactly. Knowledge, especially mathematical knowledge, is about human beings solving real-world physical problems. A society's environment, its ecology, its economy, all of that entirely dictates the kind of math it develops.
Okay, I love that framing. So if we're talking about humans solving physical problems, we have to go way, way back.
Oh, way back. Long before paper?
Right, before empires.
Right.
We need to look at the physical artifacts, the very first calculators.
Yes, the bone artifacts.
Okay.
Specifically, there are two monumental discoveries that just totally changed the timeline of mathematical history. The Lebombo bone and the Ishango bone.
Okay, let's unpack this. Let's start with the Lebombo bone. Set the scene for me. What is this thing and where did we find it?
So the Lebombo bone was discovered in the 1970s during these archaeological excavations in Border Cave.
Which is where?
It's in the Lebombo Mountains, right between South Africa and Swaziland.
Okay.
And we're talking about an artifact that dates back to roughly 35,000 BC.
Wait, really? 35,000 BC?
Yeah.
So that makes it, 37,000 years old?
Exactly. And it's basically a small section of a fibula.
The leg bone.
Right, the leg bone of a baboon. And carved into this bone are 29 clearly defined, very deliberate notches.
Now, let me push back a little here.
Sure.
Because I think a skeptic listening might say, okay, it's an old piece of bone with some scratches on it.
Nope, just an old bone.
Yeah, like maybe someone was just scraping meat off of it or absent-mindedly whittling by a fire, How do we know this is a math tool and not just prehistoric doodling?
Well, it comes down to the specific number of notches and the spacing. 29.
Okay.
That is not a random number in the natural world. It corresponds almost perfectly to the lunar cycle.
Oh, wow.
Yeah. Even today, the San people in Namibia use calendar sticks that look almost exactly like the Lebombo bone.
Really?
Yes. The pattern of dots and spaces allows someone to track lunations, the phases of the moon.
Is it literally a calendar?
It's a lunar phase counter, yes.
Yeah.
But think about the cognitive leap required to create that.
Yeah, that's huge.
We're talking about early humans making a massive transition. Because it's one thing to count physical objects sitting right in front of you.
Like, I have 3 apples.
Exactly. But it's an entirely different level of cognitive abstraction to observe a cycle in the sky, recognize the temporal pattern, and then translate that time into a sequential notation on a physical object so you can predict the future.
That is wild. You're capturing time in a piece of bone.
Precisely.
And the sources point out something really fascinating about that number 29.
Really?
Because it's tracking roughly 29 days, there is a very specific biological cycle that matches that perfectly.
The human menstrual cycle.
Right, meaning this 37,000-year-old baboon bone might literally be the world's first smartwatch or period tracker.
It's a highly compelling theory.
Which brings up this incredible hypothesis, right? That women needing to keep track of these cycles for reproduction, for survival, for understanding their own biology,
Yes.
they may have been the very first mathematicians in human history.
It's brilliant, and it perfectly illustrates our guiding principle. Necessity drives mathematics.
Right. You invent the tool because you need to solve a problem.
Exactly. The Lebombo bone gives us this visible hint of the emergence of calculation. But if we move further north and a bit forward in time, we find an artifact that is just vastly more complex.
The Ishango bone.
Yes, the Ishango bone. This was found in the 1960s near Lake Edward.
And where is that exactly?
It's in central equatorial Africa, basically right on the border of modern-day Uganda and the Democratic Republic of Congo.
Got it. And how old is this one?
It dates to somewhere between 6,000 and 9,000 BC.
Okay, so who were the people living there at the time?
They were a really established fishing and agricultural settlement. The whole community was actually buried in a volcanic eruption.
Yeah. Oh, wow. Like Pompeii.
Exactly like that, which is how the artifact got preserved. Now, when archaeologists first found it, it had a piece of quartz affixed to one end.
Like a pen.
Yeah, almost like a writing or engraving tool. And initially, they made the exact same assumption your skeptic made earlier.
That it was just random scratches.
Or just simple tally marks, A fisherman counting his daily catch. One scratch equals one fish.
But it's not just a tally stick, right? Because I was looking at the breakdown of these carvings in the source material, and the organization is incredibly deliberate.
It is deliberate, structured, and frankly, astonishingly advanced.
Walk me through it.
So the notches are grouped into 3 distinct columns, or rows, running the length of the bone.
Okay.
Let's look at the math. If you add up the notches in row A, the total is 60.
All right.
If you add up the notches in row B, the total is also 60.
Okay, so that immediately rules out random doodling.
Exactly.
You don't accidentally carve 2 separate rows of different groupings that both perfectly equal 60.
You really don't. But what's fascinating here is how they get to 60. Let's look at row B.
Okay.
The notches are grouped sequentially as 11, 13, 17, and 19.
Hold on. 11, 13, 17, 19.
Yeah.
Those are prime numbers.
Precisely. It is a complete list of all the prime numbers between 10 and 20.
Wait, really? You're telling me that thousands of years before the ancient Greeks were supposedly inventing number theory,
Yes.
a community in Central Africa was identifying prime numbers and carving them sequentially into a bone?
Yes. I mean, the statistical probability of grouping those exact 4 numbers by pure chance is vanishingly small.
That's insane.
And it gets better. Let's look at row A. It also adds up to 60, but the groupings are 21, 19, 11, and 9.
Okay, let me do the math in my head. 21, 19, 11, 9.
Think about it in relation to the number 10 and the number 20.
Oh, okay. 21 is 20 plus 1.
Right.
19 is 20 minus 1. 11 is 10 plus 1. And 9 is 10 minus 1.
Exactly. It demonstrates this clear structural understanding of a base 10 numerical system.
Wow.
They're manipulating numbers around the pillars of 10 and 20.
Okay, that alone completely changes the historical timeline of math. But the sources point out that row C is actually the most important part of the whole bone.
It is.
Why?
Because row C introduces us to an algorithm.
An algorithm on a bone.
Yes. It illustrates a method of duplication, or doubling.
How so?
The notches in this row are grouped in a sequence. It goes 3, 6, 4, 8, 10, 5, 5, 7.
Okay, let me look at the relationships. 3 doubles to 6. 4 doubles to 8. 5 doubles to 10.
Exactly. They are explicitly practicing multiplication by 2.
Okay.
But it's deeper than just a quirky way to count. This system of halving and doubling, it forms the absolute mathematical foundation of base 2 logic.
Okay, stop right there, because I want to make sure I completely understand this.
Sure.
When you say base 2 logic, assume I haven't thought about number bases since, like, middle school. What do you mean?
Well, we currently use a base 10 system.
Yeah.
Right? We have 10 digits, 0 through 9.
Right.
When we count up to 9, we run out of symbols. So we roll over to the next column, put a 1, and start over at 0. That makes 10.
Makes sense.
Base 2, or binary, only uses 2 symbols. Usually we think of them as 0 and 1.
Okay.
So when you count, you immediately run out of symbols. You are constantly rolling over, and every time you roll over, you are essentially doubling the value of the column.
Oh, I see.
And this doubling action is the exact mechanical logic that modern computers use to process data.
Wait, really?
Yes. When a computer calculates, it is rapidly shifting registers left and right.
Right.
Which mathematically is just multiplying and dividing by 2.
So you're saying the fundamental operation that allows a modern microchip to process a YouTube video or, run an artificial intelligence model is the exact same doubling operation physically carved into this 8,000-year-old bone.
Yes, it is. And as we'll see later when we talk about ancient Egypt and modern African board games, this base 2 logic didn't just stay on the Ishango bone.
It spread.
It became a persistent foundational architecture for African mathematical thinking.
That is just mind-blowing.
And there's more. An anthropologist named Alexander Marshak actually did a microscopic examination of the Ishango bone.
What did he find?
He looked at the actual tool marks, the indentations of different shapes and sizes. And he concluded it wasn't just a static math textbook.
What was it then?
It was a dynamic, highly sophisticated calendar, tracking rituals and astronomical events over a long period of time.
It's just incredible to visualize. Early humans observing the massive, chaotic physical world.
Right, the stars, the moon, the seasons.
Yeah. And distilling all of it down into this highly abstract, perfectly structured mathematical notation.
It really is.
But here's the thing about a tool, right?
Yep.
Eventually, if it's really useful, it stops being a physical object you carry around. And it becomes part of how you think.
Exactly.
As these ancient populations grew, as they migrated, as they started trading with other groups, they couldn't just pass a bone back and forth. They needed a faster way to process these numbers.
Yes, they had to internalize the logic. Which brings us to a crucial transition in the history of mathematics.
Okay.
The patterns etched into ancient bones evolved into the very words people spoke.
And that takes us right into linguistics and languages. Because math isn't just numbers on a page, it's a spoken code. We're looking at how math literally becomes embedded in the base code of human communication.
And the best way to see this is by looking at the Bantu languages.
Okay, tell me about them.
Today, there are roughly 300 Bantu languages spoken across the entire southern half of the African continent.
Wow, 300.
Yeah, we are talking about a massive geographic expanse crossing jungles, deserts, savannas.
Encompassing hundreds of distinct cultures.
Exactly.
Yet, despite all that variation in distance, the source material points out that the words for basic numbers are almost universally identical.
Yes, they are. Across these 300 languages, the word for 2 is almost always some variation of the root li, or die.
Okay.
The word for 3 almost always contains the syllable ta, or sa. And 4 is generally a nasal consonant, like ne.
So what does that tell us, mathematically speaking?
Well, it tells linguists and historians that there is a deeply rooted, shared numerical origin.
Right.
It indicates that the fundamental concepts of counting and abstract numbering were solidified long before the great dispersion of Bantu-speaking peoples.
Which originated where?
Around the areas of modern-day Nigeria and Cameroon thousands of years ago. So they had a unified mathematical language before they spread across the continent.
But the basics, like 1, 2, 3, 4,
Yeah.
that's just the beginning. The sources highlight that as these different groups settled in different environments, they developed highly complex bases for their numerical language.
Entirely depending on their economic needs.
Yeah. And this is where my mind really started to bend. Let's talk about the quinquagesimal systems.
A formidable word, I know.
It's a mouthful, but it basically just means the base 20 system, right?
Yes, exactly.
Yeah.
And we see this deeply entrenched in regions like Nigeria, Senegal, and Liberia.
Now, we talked about base 10 and base 2. Base 20 obviously means they are counting in blocks of 20, but why 20?
It's rooted in the human body.
Okay.
If base 10 comes from counting the fingers on 2 hands, base 20 comes from counting the whole body.
Oh, I see.
Right, so 5 represents a hand. 10 is 2 hands. But when you reach 20...
The phrase they use in the book is man complete.
Exactly. Because you have counted all your fingers and all your toes. The entire human unit has been tallied.
I love how visceral that is.
It's very grounded.
And the vocabulary actually scales up conceptually based on that bodily metaphor, right?
It does. So if 20 is one man complete, then 40 is 2 men complete.
Mm-hmm.
In the Malinke language, the word for 40 is dibi, which literally translates to a mattress.
A mattress. That is so funny and brilliant.
Right.
Because a mattress is where the husband and wife lie together, combining their 40 digits into one unit.
Exactly.
And it's just an incredible way to conceptualize multiplication.
It's very clever.
But, okay, as much as I love the mattress metaphor, my absolute favorite linguistic math from this research is the Yoruba system.
Oh, yes. From southwest Nigeria.
Now, as someone who grew up strictly thinking in base 10 addition, reading about this system felt like trying to write with my left hand while blindfolded.
It's very counterintuitive at first.
Because it relies on subtraction.
It is a highly demanding, highly complex cognitive system. Let's break down how it works.
Please do.
From the numbers 1 to 14, the Yoruba language functions mostly by addition.
Yeah.
So 11 is spoken as 1 more than 10.
Yeah.
12 is 2 more than 10.
Very straightforward. I'm with you.
But the moment you hit 15, the convention violently shifts.
Okay.
You stop adding from the 10, and you start subtracting from the next multiple of 20.
Wait, what?
So 15 is not 10 plus 5.
Mm-hmm.
15 is spoken as 20 less 5.
Oh, wow.
19 is 20 less 1.
Okay, I can wrap my head around that on a small scale.
Yeah.
It's kind of like how we tell time in English, right? We don't always say 2:45. Sometimes we look at the clock and say, it's 2:45.
That's a perfect analogy.
We jump ahead to the next big marker, the new hour, and subtract the difference. It's mentally efficient.
Exactly. But imagine applying that 2:45 logic not just to a clock, but to massive, massive financial transactions.
Right.
Because the Yoruba scale this subtractive logic up infinitely.
Okay, give me an example. Let's say I want to say the number 45.
To say 45 in the Yoruba language, the literal translation of the spoken phrase is an algebraic equation.
Okay.
You say the equivalent of 20 times 3 minus 10 minus 5.
Wow.
You jump all the way up to 60, subtract 10 to get to 50, and then subtract 5 to arrive at 45.
That's, wow. Okay, what about a bigger number? Say 108.
108 is expressed verbally as 20 times 6 minus 10 minus 2.
So you jump to 120.
Take away 10, take away 2.
Let me be honest here.
Sure.
Why on earth would you do that?
It sounds hard, I know.
If I'm trying to count 108 things, building it up by saying 100 plus 8 seems so much easier than jumping past the number to 120. Holding that in my working memory and then doing 2 separate subtraction equations just to tell you the number.
Right.
It sounds like a nightmare for basic counting.
Yeah.
Do they just want to make it complicated?
Well, never assume a culture develops a complex tool just to be complicated.
Fair point.
Again, go back to our guiding principle. Economics and ecology dictate the math.
Right.
The Yoruba society historically operated a bustling, massive market economy. And what was their currency?
Cowrie-shells.
Cowrie-shells, which are small physical items. Now, if you are a trader in a chaotic market and I am buying bulk goods from you, you have to count hundreds, maybe thousands of cowrie-shells very quickly.
Okay.
If you just count them one by one, adding them up, 1, 2, 3, up to 108, it takes forever.
And if you lose your place, you have to start all over.
Exactly. So how do you actually count small objects quickly?
Oh, I see where this is going.
You group them.
Yeah.
You sweep them into piles. The Yoruba traders would rapidly sweep the shells into large piles of 20.
Okay.
So if I need to pay you 108 shells, I am not counting to 108. I am making 6 piles of 20.
Which is incredibly fast.
Very fast. That's 120. Then I just quickly swipe away a pile of 10 and swipe away 2 shells. Done.
That is incredible. The subtractive language perfectly mirrors the physical action of rapidly trading bulk goods.
Exactly.
Yeah.
It requires exceptional mathematical manipulation and working memory to learn, sure.
Yeah.
But once it is internalized, it allows for incredibly fast mental math and physical trading.
And the vocabulary for large numbers gets even wilder.
Oh, definitely.
The sources mention the Igbo people. In their language, they have a specific word for 400, which is new. And if you want to square that, 400 times 400, which is 160,000.
Right.
They don't just say a big, long string of numbers. The word is nukuru nu, which translates beautifully to 400 meets 400.
It's very poetic.
It is. But, like, imagine what happens to the cognitive development of a child growing up in that culture. Before they ever step foot in a math class, their native language requires them to perform complex algebraic multiplication and subtraction just to say a number out loud.
It completely embeds abstract algebraic thinking into the subconscious language centers of the brain.
Wow.
You aren't just learning words, you are learning mathematical operations as the baseline of communication.
And it wasn't just spoken language where we see this advanced tracking, right? It was recorded in visual calendars as well.
Yes, let's move off the mainland for a second.
The Canary Islands.
Exactly. In the 14th and 15th centuries, the Guanche and Canarian populations on those islands developed a highly sophisticated mathematical astronomy. And they recorded this on something called an econo.
Yeah, the source describes the econo as looking kind of like a chessboard, painted on wooden planks or inside caves.
Right. Imagine a grid.
Yeah.
3 vertical columns and 4 horizontal rows. So 12 squares in total.
Okay, pretty simple.
It's a very simple visual interface, but it functioned as a highly accurate lunar calendar. By moving a marker or peg systematically across this board, they could perform what mathematicians call a saw function.
What does that mean, a saw function?
Well, think about the teeth of a saw going up and down.
Okay.
A lunar month is about 29.5 days. A solar year is 365.25 days. They don't line up perfectly.
Right.
If you just follow the moon, your calendar will drift out of sync with the seasons, which is, disastrous for agriculture.
You'd plant your crops at the wrong time.
Exactly. So by moving back and forth across this 3x4 grid using a specific algorithmic pattern, going up the columns, dropping down, shifting over, they created a mathematical gear that synchronized the lunar year with the solar year.
So it's essentially an ancient wooden analog computer calculating astronomical alignment.
Precisely. They used it to track solstices, equinoxes, and even the 135 moon eclipse cycle. They were also tracking the phases of the star Canopus. The math required to deduce those long-term astronomical cycles and then distill them into a 12-square board game interface is just phenomenal.
Okay, so let's take stock of where we are.
Good idea.
We have early humans mapping time on baboon bones. We have the foundational base 2 logic of modern computing carved by a lake in the Congo.
Yes.
And we have massive, bustling markets speaking in algebraic subtraction to trade cowrie shells.
Right.
Once a society has a handle on numbering systems and vast calculations like that, they don't just sit there, they start building.
They start shaping their physical environment.
Right. Which brings us to the architecture, the design, and the geometry of physical space.
Yes.
If you walk through an old European city or look at a Greek temple or even a modern American city block, you see Euclidean geometry.
Straight lines, right angles, the rigid grid.
Exactly. But when researchers started looking at traditional African architecture and design, they realized it didn't look like Europe at all.
Not at all.
And for a long time, Western observers just assumed, oh, they don't know geometry, they're just building haphazardly.
Which was a catastrophic misunderstanding of the mathematics at play.
Huge.
Because African design utilized something far more organic, nonlinear, and mathematically infinite.
We are talking about fractals.
Yes, fractals.
The source material spends a lot of time on the groundbreaking work of a researcher named Ron English.
His work is essential.
He discovered that African settlements, architecture, textiles, and even traditional hairstyles like cornrows are actually built using fractal geometry. Now, for the listener who hasn't taken advanced geometry, how do we explain a fractal?
The easiest way to visualize a fractal is to think of a snowflake, or the branches of a tree, or even the blood vessels in your own lungs.
Okay.
A fractal is a geometric pattern that repeats itself at smaller and smaller scales.
So it's like a pattern within a pattern.
Exactly. If you look at a tree, you have a big trunk that splits into smaller branches.
Right.
If you zoom in on one branch, it looks like a mini tree, splitting into smaller twigs. Zoom in on a twig, it splits into tiny stems.
Okay, fine.
It involves recursion, applying the same rule over and over again, and self-similarity. The shape looks the same no matter how close or how far away you are.
And English found this exact mathematical principle in the layout of entire African cities.
He did. He started by looking at aerial photographs of Central and West African settlements. And from the sky, he didn't see the square grids of Manhattan. He saw circular structures enclosed in larger circles. He saw rectangles within rectangles.
Let me paint a specific visual from the sources for everyone listening.
Sure.
Think of the Mukulek settlement. If you are walking through this village, you start on a wide, broad avenue.
Right.
That avenue eventually splits into smaller paths, much like the trunk of a tree splitting.
Exactly.
You follow a smaller path, and you arrive at a dwelling. The outer wall of the dwelling is a large circle. You walk inside, And the house itself is a smaller circle inside that enclosure. You walk into the house, and in the center is an even smaller circular green bin.
It is a complex, recursive, natural system.
It perfectly mimics the ecology around it.
It is a stunning visual representation of mathematical recursion.
But let me play devil's advocate here for a second.
Go for it.
Because Iglash himself initially had this exact thought. He looked at these villages and thought, is this conscious mathematics? Or is this just an unconscious social dynamic?
Right.
Like maybe people just build in circles because it's easier, and maybe the paths branch out naturally just because people take the path of least resistance when walking.
It's a valid question.
How do we know these builders are intentionally doing fractal geometry and not just building things that organically look nice?
That is the crucial question. Is it intentional optimization or just a happy accident?
Yeah.
Iglash systematically dismantled the unconscious dynamic myth by analyzing the engineering of specific structures.
Okay, give me an example.
Let's look at the Sahel region, a very arid area near the Sahara. The artisans there construct woven windscreens to protect their compounds from the blowing desert dust.
Okay, so they're weaving branches or reeds together.
Yes. But they don't just randomly stick branches in the mud. Iglash analyzed the geometry of these screens.
And what did he find?
They utilize a highly specific scaling design. They construct what engineers call active and passive lines that are carried through recursive iterations.
So the weave changes as it goes.
Exactly. The weave gets progressively tighter in a mathematically predictable pattern.
But why weave it like that? Why not just make a solid, tight wall of reeds?
Because resources are scarce. If you make a solid wall, it takes way too much material, and the wind will just blow it over.
Oh, that makes sense.
If you make it too loose, the dust gets in.
Right.
So by using a fractal scaling design, they achieve maximum dust filtration using the absolute minimum amount of effort and material.
It's aerodynamically perfect.
That is not accidental. That is intentional, conscious optimization engineering.
So they are solving a fluid dynamics problem using applied fractal geometry.
Precisely. And we see this intentional geometry extending into textiles as well.
The clock weavers.
Yes, the source details the Tellem weavers in Mali. These textiles date back to the 11th century.
Okay.
They used indigo and white cotton threads.
Now, weaving is inherently mathematical, right? You have an X and Y axis, the warp and the weft.
Yes, but the Tellem weavers weren't just making basic checkers or stripes. They were experimenting with dimensions to produce specific plane patterns.
Oh, so?
The analysis of their indigo weaves shows they were intuitively manipulating algebraic dimension formulas.
Really?
Yes. Without writing out X and Y variables, they were physically calculating translations, rotations, and reflections of geometric shapes across the plane of the fabric.
It's geometry woven into the literal fabric of society.
It truly is.
But the most mind-blowing geometric exploration in the source material has to do with a formula almost everyone learns in middle school.
Yes.
The Pythagorean theorem. A squared plus b squared equals c squared.
The theorem that allows you to calculate the hypotenuse of a right triangle.
Right, and we all attribute it to a Greek mathematician named Pythagoras.
We do.
But the scholar Paulus Gertis did some incredible research showing that African artisans discovered and visually proved this exact theorem entirely independent of and long before any Greek influence.
Yes. Gertis spent years looking at widespread decorative motifs across the continent.
What kind of motifs?
Specifically, he looked at the Chokwe people in Angola, who make these beautiful toothed square patterns.
Okay.
He also analyzed the Kuba people in the Congo Basin, specifically a tattooing pattern they call the elephant's defense, or moon.
Okay, wait. How does a tattoo prove a geometry theorem? Break this down for me, because reading an algebraic formula out loud is tough enough to follow. How do they visually prove it?
All right, let's visualize the elephant's defense tattoo pattern.
Okay, I'm picturing it.
It's a series of lines engraved or drawn on the skin that look like a grid of intersecting rectangles and right triangles. It's a very striking, sharp pattern.
Got it.
Gertis showed that if you isolate one section of this traditional design, you get a large square boundary.
Okay.
Inside that large square, the intersecting lines perfectly form a smaller, tilted square in the center, surrounded by 4 identical right triangles in the corners.
Okay, I have the picture in my head. A big square with a smaller diamond-like square inside, and 4 triangles filling the gaps around it.
Now, visually, the total area of the big outside square obviously has to equal the area of the smaller inside square plus the 4 triangles.
Right. They fit together like puzzle pieces.
Exactly.
Right.
By manipulating the length of the lines in this traditional tattoo, shifting the teeth of the pattern, you visually derive the exact algebraic relationship.
Wow.
The area of the square built on the long side of the triangle plus the area of the square built on the short side perfectly equals the area of the square built on the hypotenuse.
So they didn't write a squared plus b squared equals c squared on a chalkboard.
No.
They proved it by drawing a puzzle where the geometric pieces leave absolutely no mathematical doubt. It's a visual dissection proof.
It is an incredibly elegant proof. And Geerdes notes that by altering the number of teeth on the Chokwe squares, the artisans weren't just proving the theorem once.
What do you mean?
The algorithm of the pattern generates an infinite number of proofs for different proportions.
This makes me think about that classroom we talked about at the very beginning.
Right.
The source material points out how Ron English actually took these African fractals and created educational software.
He did, yeah.
He made a program that models traditional cornrow hairstyles using fractal algorithms.
Amazing.
So imagine a student who is struggling with abstract algebra. Instead of forcing them to memorize a dry formula from a textbook, you show them the hairstyle they might literally be wearing or the patterns woven into their family's traditional cloth, and you say, model this mathematically. It completely changes the paradigm.
It grounds the abstraction in a tangible, deeply cultural reality. It says, your ancestors were doing this math. You already have this in your cultural DNA.
Yeah.
Now, if we look at how societies scale over time, we reach a very important transition.
Right. Because we've seen how intuitive geometry was woven into cloth and how complex subtraction was used in local markets. But eventually, populations boom, villages become cities, cities become empires.
Yes.
And when a society scales up to an empire, one that needs to tax millions of citizens, manage massive agricultural yields, and build monumental architecture.
That intuitive physical math has to be codified.
Exactly. It has to become rigid, standardized, and written down.
And that transition takes us down the Nile River to section 4 of our exploration, the written record, ancient Egypt, and the mechanics of empire.
Now, I want to address an elephant in the room here.
Let's do it.
Because sometimes historians or textbooks try to culturally separate ancient Egypt from the rest of Africa.
Right. They treat it almost like a Mediterranean or European outpost.
Exactly. But the sources we are looking at explicitly state that you cannot racially, culturally, or geographically separate Egyptian civilization from its Black African roots.
That is a critical point. The mathematical traditions we just discussed, the base 2 logic from the Congo, the geometric explorations from the south and west, they flowed north down the Nile. Egyptian mathematics did not spring out of nowhere. It is the codified culmination of the deep African mathematical continuum.
And we know exactly how they codified it because we have the receipts, we have the papyri.
Yes. The most famous is the Ames Papyrus, often called the Rhind Papyrus, which dates back to around 1650 BC.
Okay.
We also have the Moscow Papyrus from roughly 1850 BC. These documents give us a direct look into the minds of Egyptian administrators and mathematicians.
Let's talk about how they actually wrote numbers down, because their notation system went through a fascinating evolution.
It did.
They started with hieroglyphics, which were pictorial.
Right. If they wanted to write the number 1, they drew a simple vertical stroke. A 10 was a horseshoe shape, 100 was a coiled rope, 1,000 was a stylized lotus flower.
And my absolute favorite, a stylized tadpole represented 100,000.
Yes, the tadpole.
Imagine being an accountant and having to draw a little frog every time you calculated taxes.
It would take forever.
Right. Obviously, that takes a long time to carve it into stone or paint on a wall. So for administrative efficiency, they had to invent a faster way to write.
They developed hieratic notation and later demotic notation.
What did those look like?
These were highly symbolic cursive scripts that were much faster to write with a reed pen and ink on papyrus. It allowed the bureaucracy to function at high speed.
But the most revealing thing about Egyptian math isn't just how they wrote the numbers, it's how they calculated them.
Yes.
Let's look at Egyptian multiplication. Because they didn't memorize massive times tables like we do.
No, they didn't.
They multiplied using a system based entirely on doubling.
Exactly. To multiply any 2 numbers together, no matter how large, an ancient Egyptian scribe only needed to know 2 things.
What were they?
How to add and how to multiply by 2.
That's it. Okay, stop and explain this to me like I'm 5. Walk me through a physical example. How do I multiply 15 by, say, 12 using only doubling?
Okay, you want to multiply 15 by 12. You set up 2 columns on your papyrus.
Okay. Drawing column.
In the first column, you always start with the number 1. In the second column, you write your multiplier, which is 12.
Got it. Column A is 1, column B is 12.
Now, you just double both columns. Under the 1, you write 2. Under the 12, you double it to 24.
Okay.
Then you double the next row. The 2 becomes 4. The 24 becomes 48. Double it again. The 4 becomes 8. The 48 becomes 96.
Okay, so column A reads 1, 2, 4, 8. Column B reads 12, 24, 48, 96. How does that get me to 15 times 12?
You look at column A. You find the numbers that add up to your target, which is 15.
Okay, what adds up to 15? 8 plus 4 plus 2 plus 1. You need all of them.
Exactly. So you just add up the corresponding numbers in column B, 96 plus 48 plus 24 plus 12.
And the total is 180.
Which is exactly 15 times 12.
That is incredible. They bypass complex multiplication entirely just by breaking the number down into binary building blocks.
Yeah. In modern mathematical terms, they were expressing the number as the sum of powers of 2. 2 to the third plus 2 squared plus 2 to the first plus 2 to the 0.
And wait, where did we see this exact same halving and doubling math earlier?
The Ishango bone.
From Central Equatorial Africa thousands of years prior.
This is why we say Egyptian math is intrinsically African. The Egyptian doubling method is just the codified, written version of the base 2 logic carved into that bone.
It's all connected.
Furthermore, it is exactly how a modern computer processor multiplies.
Like we said before.
Right. A computer chip doesn't know what 15 times 12 is.
Yeah.
It simply shifts binary registers left and right, halving and doubling voltages until it gets the answer.
So the pharaoh's accountants were acting as organic binary computers?
Pretty much.
But the Egyptians had one quirk that I find absolutely baffling.
Let me guess.
It's their use of unit fractions.
Ah, yes. The unit fraction obsession.
From my understanding, they only liked to use fractions where the numerator, the number on top, is a 1.
Yes.
So they would use 1/2, 1/4, 1/7, 1/15. But if an answer was 3/4 or 5/7, they wouldn't write it like that.
We would break it apart into a massive string of unit fractions.
Why? Why make it so insanely complicated?
So again, we have to look to the economy. Ancient Egypt, for much of its early and middle history, was fundamentally a moneyless economy.
Okay.
They didn't have a standardized coin currency. All transactions, all taxes, all wages were paid in kind. Physical goods.
Okay, so you're paying people in grain or beer or bread.
Exactly. Imagine you are a foreman and you have exactly 7 loaves of bread. You need to divide them equally among 10 workers. You can't just hand someone 7/10 of a loaf. You have to physically cut the bread.
Okay, so I cut all 7 loaves in half. Now I have 14 halves. I give 1/2 to each of the 10 workers. Everyone has half a loaf, but I still have 4 halves left over on the table.
Right. Now you take those 4 leftover halves and you cut them into thirds. That gives you 12 smaller pieces.
Okay.
You give 1 to each of the 10 workers. Now everyone has 1/2 plus 1/15 of a loaf.
Oh.
You see what's happening. You are physically whittling down the goods into highly precise unit fractions.
It was a perfectly equitable way to divide physical space and physical goods so that no worker felt cheated.
Exactly. If you were running an empire, avoiding labor riots over bread is a top priority.
That completely demystifies it. It's not abstract math, it's a slicing algorithm for physical reality.
Right.
And to handle this, the sources say the mathematicians created massive lookup tables, figuring out how to break down any odd fraction into these unit fractions. They used something called red auxiliaries.
Yes, the scribe would write certain intermediate numbers in red ink.
What were they for?
Functionally, it was an ancient method of finding the lowest common denominator to solve what they called problems of completion. It was brilliant algebraic accounting.
But they weren't just accountants. Their geometry was astonishing.
Yeah, absolutely.
If you are building the pyramids, you need precision. The sources show they accurately approximated the area of a circle.
They implicitly estimated pi to be about 3.1605.
Which is incredibly close for the ancient world.
It is.
But the masterpiece is their formula for the volume of a truncated square pyramid.
The frustum, yes.
Imagine a massive pyramid, but you chop the top third of it off. You just have a flat top base, a wider bottom base, and slanted sides.
Right.
The Egyptians figured out the exact formula to calculate the three-dimensional volume of the space inside that shape. How did they do it? Because historians seem to debate this.
it's still a point of passionate debate among historians of mathematics.
Yeah.
They didn't have modern algebra.
So what did they do?
Did they conceptually slice the stone block into smaller, easily calculable geometric pieces and sum them up? Did they use what we call the Huronian mean of the base areas?
It's crazy to think about.
Whatever physical or conceptual method they used, it required a level of spatial reasoning and algebraic sophistication that is truly breathtaking.
And again, it comes back to the environment. The Greek historian Herodotus actually wrote about this.
He did.
He traveled to Egypt and wrote about how Pharaoh Ramses II taxed square plots of agricultural land. The problem was the Nile River.
The flooding.
Every single year, the Nile would flood. It brought vital nutrients to the soil, but it completely washed away all the property markers.
Which is an administrative nightmare. If your land shrinks because the river washed part of it away, you shouldn't have to pay taxes on the land you lost.
Right. So the pharaoh sent out surveyors. They call them rope stretchers because they literally used knotted ropes to measure. They had to go out into the mud, remeasure the newly shaped irregular land, and calculate the exact geometric area so the farmers could get a tax write-off.
It's fascinating.
Necessity, literally a river washing away your property lines, forced the invention of advanced surveying geometry.
And this leads to a vital point about the historiography of math.
Yeah.
Herodotus wrote this down. The Greek mathematician Democritus openly praised these Egyptian rope stretchers, admitting that nobody, not even him, surpassed them in geometric construction.
Right.
We know Pythagoras likely traveled and studied in Egypt. The Greeks openly acknowledged their debt to African mathematics.
Yet, somewhere along the line, the modern world developed a massive historical blind spot.
A huge one.
We wrote Africa out of the textbooks and credited the Greeks with inventing rigorous math out of thin air.
But the truth is, the mathematical torch never went out. Even as the era of the pharaohs faded and the center of power shifted, the research continued.
It simply moved west.
Which brings us to Section 5. The Golden Age of North Africa, or the Maghrebian tradition.
We are moving from the 9th to the 18th centuries. Geographically, we are in places like modern-day Morocco, Algeria, and Tunisia.
In the Maghreb, we see a massive evolution. Mathematics shifts from the physical administration of land and bread into high-level abstract algebra, number theory, and most importantly, combinatorics.
The sources outline a few heavy hitters from this era. Let's start with Abu al-Qasim al-Qurashi in the 12th century.
Yes.
He became an absolute master of algebra, specifically to solve Islamic inheritance law.
Inheritance law in Islamic jurisprudence is famously complex.
I can imagine.
It determines exactly what specific fraction of an estate goes to a son, a daughter, a brother, a widow, under highly specific conditions.
Right.
If a wealthy merchant dies, dividing the assets legally is a staggering mathematical puzzle.
So, just like the Egyptians needing to divide bread, the Maghrebian scholars needed to divide wealth without breaking the law.
Exactly.
Al-Qurashi developed a new algebraic method based on decomposing numbers into prime factors to reduce all those complex inheritance fractions to the same denominator.
Real-world legal problems driving pure mathematical innovation.
Then we have Al-Hassar, another vital figure. He wrote a text called The Book of Proof and Recall. This book is critical to modern math because it introduces the symbolic writing of fractions using a horizontal bar, the exact way we write fractions today.
It also popularizes the dust ciphers, which are the direct ancestors of the numerical digits 0 through 9 that the whole world uses right now.
But the figure who absolutely blew my mind was Ibn Munjim. He lived in Marrakech in the 12th century.
His work is incredible.
And he did groundbreaking work in a field called combinatorics. Now, for the listener, combinatorics is the science of counting, arranging, and finding the probabilities of different combinations. It's the math of permutations.
Yes.
And Ibn Munjim set out to solve a massive problem. He wanted to mathematically enumerate all the possible words that could be created in the Arabic language using its 28 letters.
It is a colossal computational task. To figure out all the permutations of vowels, consonants, and syllable structures without a computer is almost unimaginable.
So how did he do it?
He built a concrete physical model.
The text says he used different colored silk threads.
Yes. Imagine a scholar in the 12th century sitting in a study in Marrakech, surrounded by spools of colored silk.
Okay.
He would use a red thread to represent one linguistic rule, a blue thread for another, a green thread for vowels.
Let me make sure I'm visualizing this right. It's almost like he was building a physical flowchart out of string.
Exactly.
If you pull the red string, it physically maps out one combination of letters. If you cross it with the blue string, it shows another branching path. He essentially built a physical, tactile calculator out of silk to map data permutations.
That is a brilliant analogy, yes. He built a three-dimensional web of data, but again, we have to ask why.
Right.
Why dedicate your life to the combinatorics of language?
Because Maghrebian math wasn't born in a vacuum. It wasn't just math for math's sake.
Exactly. It was driven by the deep cultural and religious importance of linguistics. Scholars needed to formalize Arabic grammar, determine the exact rules of poetry meters, and ensure the absolute correct pronunciation of sacred texts.
The culture demanded a mathematical understanding of language.
And that research didn't stop with him. His student, a man named Ibn al-Bana, who was born around 1256, took this combinatorial math even further.
What did he do?
He actually announced and mathematically demonstrated the formula for factorials.
A factorial is when you multiply a number by every integer below it. So 5 factorial is 5 times 4 times 3 times 2 times 1.
Exactly. He figured out the exact algebraic formula for finding the combinations of anjeks taken p at a time.
And the kicker, he published this 300 years before the famous European mathematician Blaise Pascal, who almost always gets the credit in modern textbooks.
Ibn al-Bana was wildly prolific. He wrote over 100 works. But one of the most fascinating is a text called Advertisement to the Intelligentsia. In this book, he didn't just deal with high-minded theory. He applied this advanced combinatorics to everyday, highly specific practical problems.
Give me an example. What kind of daily problems required advanced factorials?
Well, he calculated the exact legal tax required for a delayed payment in complex trade agreements.
Okay.
But my favorite example is religious. He used combinatorics to calculate the exact number and order of prayers a Muslim needed to say to perfectly compensate for a specific number of forgotten prayers over a long period of time.
Wait, really? So if I forgot to pray a few times over the last month, I can't just throw in a few extra prayers and call it even?
According to strict jurisprudence, no. You had to account for the specific sequence and timing.
Wow.
Ibn al-Bana used high-level combinatorial math to give people the exact formula for spiritual restitution. He was applying cutting-edge mathematics to religious devotion.
That is profound. And this knowledge wasn't isolated, it bridged directly to Europe.
It absolutely did.
The famous Italian mathematician Fibonacci, the guy famous for the Fibonacci sequence, he didn't invent this stuff in Italy. He traveled and studied in Bougie, in modern-day Algeria. He sat in these Maghrebian schools, learned their fraction symbolism, their algorithms, their algebra, and he took it all back to Europe in his famous book, Liber Abbasi.
Yes.
The roots of the European mathematical renaissance literally passed through the markets and universities of North Africa.
It is an unbroken chain of knowledge. However, as historians, we also have to look at the fragility of scientific progress. The sources point out that this magnificent golden age of Maghrebian research eventually contracted.
Why did it stop? Did they hit a mathematical wall?
No, they hit a geopolitical wall. The Maghreb suffered a massive political and economic decline.
Oh.
They lost control of the vital trans-Saharan gold routes. At the same time, they faced relentless naval offensives and blockades from rising European powers like Spain and Portugal.
So the economy collapses and the math suffers.
Precisely. When cities are under siege and trade routes dry up, society starts funding abstract scholars. The research contracted.
That makes sense.
Instead of inventing new theories, the scholars just started writing repetitive teaching manuals to preserve what they already had. It's a stark reminder of how dependent scientific advancement is on political and economic stability.
That is a tragic note, but it leads to the final and perhaps the most mind-blowing part of our journey today.
Yes, it does.
Because while the elite university-level scholarly research in the cities may have contracted, that deep, complex mathematical thinking never left the people.
It didn't disappear. It embedded itself deeply into the culture, specifically into their leisure activities.
This brings us to Section 6, the mathematics of play, combinatorics, and board games.
We just talked about elite scholars in Marrakech calculating factorials with silk threads.
Right.
But the beautiful thing about African mathematics is that these dizzying combinatorial concepts were actively being calculated in the dirt on the side of the road by everyday people.
We are talking about the tradition of African board games. Now, outsiders and Western anthropologists generally group all these games under the umbrella term Mancala, but they have hundreds of distinct local names and variations. Today, we are going to focus specifically on the game of Ayo, played by the Yoruba in Nigeria, and Omweso, played in Uganda.
Now, for the listener who has never seen one of these games, let's walk through the physical mechanics.
Yeah, let's do that.
Imagine a beautifully carved wooden board sitting between two players. On the board, there are rows of small pits or bowls hollowed out of the wood.
Right.
In some places, they don't even use a board. They just scoop holes directly into the hard-packed earth. And instead of chess pieces, you use counters.
Yeah.
Usually small seeds or stones or cowrie shells.
The basic mechanic of the game is called sowing. You pick up all the seeds from one of the pits on your side of the board, and you drop them one by one into the consecutive pits, moving around the board.
It sounds incredibly simple.
Yeah.
You scoop, you drop, you scoop, you drop.
It sounds simple until you look at the rules of capture.
Right.
The goal is to capture your opponent's seeds, and this is dictated by highly specific rules regarding exactly where your very last seed lands.
Does it land in an empty pit? Does it land in a pit with an even number of seeds? This determines the outcome.
And crucially, there are no dice. There are no cards. There is zero element of chance.
None. It is a game of pure, unadulterated intellect, abstract thinking, and strategy.
Let's deep dive into Omweso, the Ugandan variation. They hold massive tournaments for this in Kampala. Omweso is what mathematicians call a re-entrant game.
A re-entrant game means that when you capture your opponent's seeds, you don't just take them off the board and put them in your pocket.
What do you do with them?
You immediately take those captured seeds and replay them, sewing them back into your side of the board on that exact same turn.
Oh, wow.
You start the game with 64 seeds in play, and all 64 seeds remain in play for the entire game, constantly shifting matrices.
The complexity of that is staggering. If I capture your pieces and immediately replay them, it creates a cascade, a chain reaction. The source material uses two specific mathematical metrics to measure just how complex Omweso is. The first is called state space complexity. What does that mean?
State space complexity measures the total number of possible legal positions the pieces can be in on the board.
Okay.
For a game like tic-tac-toe, that number is very small. For Omweso, the state space complexity is calculated at 5.6 times 10 to the 23rd power.
Let me translate that for the listener. That is a 5, followed by 23 zeros. It's an almost unfathomable number of board configurations.
And the second metric is even larger. It's called game tree complexity.
Okay, what's that one?
This measures the total number of possible game paths. If I make this move, you have 15 possible responses, and for each of those, I have 15 responses branching out like a massive tree from the first move to the end of the game.
Oh, wow.
Factoring in the branches per turn and the average game length, the game tree complexity of Omweso is roughly 5 times 10 to the 50th power.
Okay, pause. Pause and let that sink in. 5 times 10 to the 50th power decision branches.
Massive.
Now picture a bustling street corner in Kampala. Two men are sitting over a wooden board. In tournament play, they are only allowed 3 seconds of thinking time per turn. If you hesitate, if your hand stops moving, the referee calls a foul, and you lose your turn. These players are navigating a decision tree of 5 times 10 to the 50th power, and they are making their move in under 3 seconds.
That is raw, real-time processing power that legitimately rivals a modern supercomputer.
It truly is.
When mathematicians and computer scientists break down the physical operations of the game, they realize the players are constantly doing rapid shift, add, and subtract operations.
Right.
They're intuitively recognizing complex symmetrical series across the board. The Omweso board is essentially a 4x8 matrix. Researchers studying the gameplay have actually found magic numbers naturally embedded in the dynamics of that matrix.
Magic numbers, like what?
Numbers like 0, 2, 8, 9, 17, and 25. These specific numbers continually dictate the outcomes of diagonal and row differences on the board. The expert players have internalized these geometric and numeric relationships. When their hands are flying across the board, they aren't just playing a game. They are executing complex loop functions and matrix mathematics in real time.
The ultimate flex in Omweso, the move that crowds gather around to watch, is something called cutting off at 2 heads.
Oh, yeah.
Imagine the board state. In a single, devastatingly calculated move, a player drops a seed that triggers a capture. Because it's re-entrant, they immediately replay those seeds, which triggers another capture, which triggers another. They set off a chain reaction of sowing and relaying that systematically sweeps across the board and captures seeds from both extreme opposite ends of the opponent's territory simultaneously.
It's a breathtaking display of organic computational power.
To pull that off, the player had to visually calculate a complex algorithmic loop, dozens of steps in advance, all within 3 seconds.
We see similar mathematical brilliance in the IO game in Nigeria. Researchers have analyzed what they call determined positions in the IO endgame.
What's a determined position?
It means that a highly skilled IO player can mathematically force the board into a specific state where the outcome is entirely predetermined by an algorithm.
Really?
Yes, they can calculate a sequence where they capture stones on every single successive turn, completely neutralizing the opponent's ability to respond.
Whoa.
They trap the opponent in a mathematical loop, forcing them to leave exactly one stone on the board at the bitter end. It's not luck. It's an algorithm of total domination.
And here's the fact that ties this entire deep dive together. The sources note that right now, in modern tech labs in Silicon Valley and around the world, computer engineers are using these exact African board games to train artificial intelligence.
Yes, they are.
They are feeding the rules of Mancala and Umweso into machine learning models to teach AI how to navigate 10 to the 50th game tree complexities and improve their decision-making logic.
It highlights a beautiful, almost poetic irony. The absolute cutting edge of modern artificial intelligence is currently being trained on the algorithms of ancient African leisure activities.
Which brings us full circle. Let's synthesize exactly what we've discovered today. We started by looking at an educational system that tells students that math is a foreign Western concept. But then we looked at the evidence.
We saw the 37,000-year-old notches on the Lebombo bone tracking the phases of the moon. We saw the undeniable base 2 doubling and prime numbers of the Ishango bone.
We explored the complex algebraic subtractive counting of the Yoruba market economy, counting massive sums of cowrie-shells. We zoomed in on the conscious, mathematically optimized fractal layouts of Sahel villages and Kuba textiles.
We witnessed the precise geometry and fraction tables of the Egyptian rope stretchers dividing the land after a flood. We unraveled the colored silk threads of Maghrebian combinatorics, mapping the Arabic language.
And finally, we watched the dizzying matrix algebra of street games like Umweso, calculating billions of possibilities in 3 seconds.
Yeah.
What we are looking at is not a fragmented history. It is a rich, unbroken, and highly sophisticated mathematical continuum. It completely shatters the myth that rigorous mathematics was solely a European invention.
The history of mathematics is not a straight line drawn from Greece to Europe. It is a vast, ancient, and incredibly vibrant tapestry.
Yeah.
And the thickest, oldest threads are woven directly across the African continent.
So we want to leave you with a final provocative thought to mull over. As we move deeper into this modern age of artificial intelligence, complex algorithms, and quantum computing, we are culturally conditioned to view these technologies as modern, purely Western triumphs.
Right.
But knowing what you know now, look at the foundation. What if the deepest roots of binary logic, recursive algorithms, and machine learning are unconsciously sitting on a foundation built tens of thousands of years ago by African weavers, astrologers, linguists, and game players?
The next time you see a computer processing a massive complex loop or an AI navigating a massive decision tree, ask yourself, is it just running modern code or is it playing a digital game of Mancala?
Look around you today. Look at the branches of the trees, the layout of your streets, the way you count your money. Find the hidden math, the fractals, and the algorithms and the patterns of your own daily life. The history of human calculation belongs to all of us. Keep questioning the narrative, keep digging into the past, and we'll see you on the next deep dive.